Most welcome to 1174 of the series, and I hope you are all enjoying yourself. Let's pour my cup of tea here. We had some rain, so the incredible sunny weather of September is coming to a halt. It's been way too warm. Way too warm. Not good for the vegetation, I'd say. And last time I started with chapter 1, and as you might remember, I was quite happy start a little bit, going back a bit here. Shortcomings of the outside-in approach, something I mentioned. Inside out and outside in. The prevalent today is without a doubt the outside in. That has been a thing for at least the last 2-3 millennia. And that has gone into our language, into our veins. It is in the web of talking, thinking, understanding. Every time we mention something, it is almost bound to stir memories that goes in that connection. György claims that this has hampered science, neurology, cognition, and as we know, this is a view shared by Paul Feyerabend and many others, critics of the dogma. But what the dogma is, I think, doesn't become understandable completely until we enter the subject. And this is what György is doing. Shortcomings of the outside-in approach. Ever since John von Neumann's comparison between the computer and the brain, computer metaphors have dominated. I think I better move. Sorry about that. Let's start again here. Shortcomings of the outside-in approach. Ever since John von Neumann's comparison between the computer and the brain, computer metaphors have dominated the language of neuroscience. A metaphor is a powerful tool to convey an idea because it relates a mysterious phenomenon to an understood one. However, metaphors can also be misleading because they may give a false sense of understanding a novel phenomena before it is actually known how the things works. In the brain-computer metaphor, neuronal operations are likened to the machine's ability to transduce a real-world thing into symbols called representations. By this logic, symbols in the real brain, the firing patterns of neurons, for example, should correspond to some real-world stimuli, in the same way that computer algorithms correspond to or represent inputs from the objective world. However, unlike in the computer, the same stimuli often induce highly variable responses in the brain depending on brain states and testing conditions. We often pretend that we know which features interest the brain and correlate them with neural activity. Such arbitrariness is appropriate and in fact essential for symbolic representations by machines because they are trained to produce a best match between experimenter-chosen features and symbols. But brains are different. Representation of the objective world and finding truth are not their main job. The brain evolved not to represent anything, but to help its host body to survive and reproduce. In addition, brains produce many effects that do not correspond to anything tangible in the physical world. Pleasure and fear, desire, irrational numbers, or the entire discipline of math, and even Santa Claus, feel real without corresponding to something veridical outside the brain. According to the outside-in framework, the best strategy to understand mechanisms of perception and cognition is to present various stimuli, an object or aspects of an object, and examine the spatiotemporal distribution of the evoked neural responses in the brain. To increase the rigor of discovery process, initially simple stimuli are presented, such as vertical and horizontal gratings for vision or beeps of particular frequencies for hearing research. After the data are collected and interpreted, researchers can search for neural responses to increasingly complex stimuli. This strategy anticipates that one should be able to explain how an object is represented in the brain from the observed relationship between the stimuli and the neural responses. The research program was pioneered by legendary scientific duo David Hubel and Torsten Wiesel, the Nobel Prize winners in physiology and medicine in 1981, who introduced single neuron recordings to study the visual system. They made a long series of extraordinary discoveries that continue to influence sensory research today. The theoretical framework of passively associating brain was a welcome strategy to experimenters because neural responses to sensory stimuli could be registered also in anesthetized or paralyzed animals. There's a short note here. Representation is a Platonic concept referring to the idea that we humans cannot comprehend the real world, Kant's noumenon, but only a representative of it, phenomenon. Both in classical Cartesian dualism and Lockean empiricism, the mind relies on the representation of noumena. When experiments were subsequently performed in waking animals, their heads and even the eyes were fixed to eliminate inconvenient behavior-induced variability in the recorded brain signals. However, building a complex percept in the brain from its assumed elementary components turned out to be a formidable hurdle given the astronomical realm of possible combinations. Luckily, it turned out that natural visual scenes and sounds represent only a small subset of all possible combinations. So sensory researchers recently began to use natural images and sounds. They discover that brains are fine-tuned for naturally occurring stimuli, and thus many aspects of neural activity were missed with the previous artificial stimuli. For example, even in a small brain like that of a frog, transmission of acoustic information is most efficient when the spectrum of sounds matches the spectrum of natural frog calls. But the nature of the stimulus is only a technical problem. The bigger issue is that the brain is not a passive device that unconditionally associates signals. A tacit assumption of the outside-in framework is that attributes or features of objects are bound together by some brain mechanism. What makes an object an entity is the coherent fusion of its components, which separate it from its surroundings. For example, a car has a particular shape with a body and wheels, color, sound, and a characteristic movement pattern. But there is a problem with this philosophy, which is that the attributes of an object are not fixed set that reside in the object, but are constructed in the brain of the observer. Brain responses do not intrinsically represent stimuli until the experimenter interprets the data. Judgments of similar or different are subjective, that is, observer dependent. Yes, an experimenter can quantitatively define the relationship between stimuli and the spatiotemporal firing patterns of recorded neurons. However, this relationship does not mean that neurons in the brain of the experimental subject views the stimuli in the same way as the experimenter. Nor does it mean that the brain uses these recorded signals in the same way or at all. This is the crux of the problem of the outside-in coordinational approach. It cannot yield adequate understanding of perception or neuronal computation. I briefly summarize the outline of this argument here and return to it in more detail later on. Only action can provide meaning to brain activity. Like the philosophical issues that plagued physics through the 20th century, the issue in neuroscience is the observer. There is a fundamental difference between an observer outside the brain, such as the experimenter, and an observer inside the brain, such as Descartes' hypothetical homunculus residing in the pineal gland. First, let's take the perspective of an experimenter studying the visual system. Upon presentation of visual stimuli, an image is converted to action potentials by retinal ganglion cells and conveyed to the primary visual cortex via neurons in the thalamic lateral geniculate body. The experimenter can place a recording device, such as an electrode array, inside the brain and monitor neural responses to different images presented to the eye. In this situation, the experimenter has a privileged point of view. He has access to both the images, external world, and the neural responses in the brain. From this perspective, and I would say in parentheses from this perspective only, he can find a reliable correlation between specific features of the presented images and neural responses, which allows him to make a guess about the possible input-output transformation rules. After establishing a correlation, often mistakenly called a neuronal code, he can recover stimulus properties from the neuronal responses and even predict the properties of untested stimulus patterns. In short, a particular constellation of neuronal spike patterns becomes information. But to whom is that information useful? The recorded signal in the brain, combined with a priori knowledge about the stimulus, can generate meaning only to the experimenter. Very, very important. Only to the experimenter. The death toll of Cartesian dualism here. It is a death knell. Bye-bye, Descartes. You are gone now, I would say. This is probably the strongest argument and easiest to understand. I will reformulate later on, but it is vehemently clear, if you excuse that term. The observed correlation between the image and neural response only means that something outside the brain was transformed into firing pattern changes. What about internal observers, the brain circuits? The neurons that respond to the image do not see the image, just patterns of neural spiking arriving from their peer neurons. Neurons in the visual cortex are blind to events that happen in the world, and so is the rest of the brain, or even a magical homunculus watching the action of all visual cortical neurons. Imagine that the little human is the experimenter who, in a magic experiment, can register the activity of all neurons in the brain. Without access to information outside the skull, such knowledge cannot, listen carefully, cannot reveal what the brain is sensing. It cannot see whatever is out there. In the language of neural code, the outside-in framework has shown only that decoding of stimulus properties from neural activity is possible in principle, only if an observer has the codebook. However, the brain only has its own neural responses, and the outside-in framework does not mention how such a code would be generated or read by neural responses alone. Hooray for György Buzaki. This is well worth repeating. It is between page 16 and 17. Try to make a copy of it, otherwise go look for it. These are strong words, and they are very, very clear. If you don't understand here, I think no one can resist understanding here. This is really a spearhead going into the Cartesian homunculus itself. Yes, it's an it. All any neuron in the brain ever sees is that some change occurred in the firing patterns of its upstream peers. It cannot sense whether such change is caused by an external perturbation or by the brain's perpetual self-organized activity. Thus, neurons embedded in networks of other neurons do not know what the brain sensors are sensing. They simply respond to the upstream inputs. In other words, unlike our ideal experimenter, the neurons have no way of of relating or comparing their spikes to anything else because they only receive retinal correspondences or processed representations of sensory input. But establishing correspondences without knowing the rules by which those correspondences are constructed is like comparing Mansi words with Kanti words when we understand neither language. Mansi is actually related to Hungarian. I think György Buzaki, being in Hungarian, mentioned that specifically. Only after we have defined the vocabulary of one language can we understand the corresponding meaning of words in the other. Similarly, without further information, sensory neurons can attach no meaning whatsoever to their spikes. Put it simply, the mind's eye is blind. To explain my point differently, let me invite you to do a thought experiment. Let's connect the output of a video camera to cultured neurons in a dish, derived from the visual cortex of the smartest person in the world, so that a fraction of the neurons is stimulated by the camera output. The part of the tissue culture that is stimulated by the camera output can be called sensory region. Sorry, I just realized that I should download this. What we call in Swedish a konstpaus. The part of the tissue culture that is stimulated by the camera output can be called the sensory region. We may discover that repeated visual patterns, such as the picture of the rose, will induce somewhat similar neuronal responses. We may even detect some changes in synaptic connectivity among neurons as a result of repetition. It is also possible, though, that some members of the cultured neuronal network will be preoccupied with each other and ignore the stimulation altogether. The experimenter can establish a relationship between the applied stimuli and the corresponding neural responses and declare that some coding was identified. But the tissue culture does not see, well, I know, I understand. The tissue culture does not see the rose or the image or whatever is out there. So far, this analogous to the passive representational brain model and the experimental approach used in many laboratories. Since the neurons in the culture have no direct access to the outside world, they have no way of verifying or grounding their patterns to the events outside. The term grounding refers to the ability of the brain circuits to connect it to something meaningful for the owner of the brain. It's kind of a second opinion from a more reliable source. Using our dictionary metaphor, if you know the meaning of words in an English dictionary, you can ground the meaning of corresponding words in a dictionary of any other language. The situation in the dish may change dramatically if the spiking output of some neurons is connected to a robot that can move the camera based on the spiking patterns of these experimenter designated motor neurons in the culture. Now neurons in the dish have two functions. One function is generating an output, move the camera, and the second is responding to the camera supplied signals. Because the tissue culture circuit is supposedly well interconnected, neurons in the sensory region will receive two types of inputs: input from the camera signals and an additional input from the motor neuron partners, which inform them that it was their action that induced movement of the camera and therefore changes in the sensory input. Now we have a closed loop system in a dish, an output-driven sensory feedback device. The addition of the robot provided the cultured neurons with the same advantage as the experimenter. Now, the neurons can sense both the outside world and the internal computation, and therefore can compare their joint impact. Now let's assign a goal to our closed loop system. For example, to find the rose in the picture. There's a picture here of a rose. We call it an image. Whenever the camera is focused on the image by the chance behavior of the cultured neurons, a magic potion is spritzed onto the culture to strengthen the connections between those neurons that successfully move the camera to the desired spot in the visual scene and the neurons that were activated by the rose. This simple modification may increase the probability that such neural activity will happen again and lead to pointing the camera at the rose more often. Thus, out of the large realm of possible neural network patterns, at least one unique event acquired a meaning. You see, meaning is only when you have the coupling of something being observed and the observer. This shows without that coupling there is nothing. And I think this is the thumbs down also for classical mechanical ideas. Don't confuse their usefulness with their truthfulness. Don't do that. Remember that. Useful is not the same as truthful. This is truth. Buzaki has put his finger down on something incredibly important. Thus, by connecting a bunch of otherwise useless tissue culture neurons with the world through an action perception arc, we have just built a machine with a purpose, a brain-like device. In fact, we may not need a magic potion if we assume that the brain is already pre-wired to some extent so that its connectivity is not random but guided by some evolution-shaped statistical rule. The internal feedback from action-induced neurons to sensory neurons may be regarded as a second opinion, the needed grounding signal that can attach meaning to input-induced neural responses. In our tissue culture example, we arbitrarily design two sets of neurons and call them sensory input to where the stimuli from the camera were delivered and the motor output because these neurons were connected to the robot moving the camera. The tissue culture has no a priori bias toward these designations, and the two areas are reciprocally interconnected to each other. In real brains, the sensory and motor areas have somewhat different internal connectivity, but the similarities are more striking than the differences. The differences are even more blurred when we compare the partner structures, often referred to as higher order sensory and supplementary motor areas. These areas are reciprocally connected, and the traffic moves not only from the sensory to the motor circuits, but equally so from a motor to the sensory areas. This latter motor to sensory projection has a fundamental impact on many levels of brain operations, as we will see in the following chapters. The picture I just painted is unfortunately an oversimplification. I did not mean to create the impression that tissue culture thought experiment can explain the mechanisms of thinking, of a thinking, feeling brain. It was only meant to illustrate the minimum necessary requirements of a brain-like system. Random connections and plasticity are not enough. A large part of brain structure is genetically determined, and self-organized activity is as important for the development of brain dynamics as is sensory stimulation, even in primary sensory areas of the brain. The inside-out reader-centric framework. Can James's table of contents and the outside-in strategy be renegotiated? I do not think it would get us very far. My point is not that measuring brain responses to stimuli yields no valuable data or insight. In fact, a primary slogan in my laboratory is that it is impossible to find nothing in the brain. An enormous amount of pressures An enormous amount of precious knowledge has been obtained by identifying neuronal correspondences and representations of the sensory world over the past decades. Until recently, the empiricist outside-in approach has generated most of the available knowledge about sensory coding, and it continues to be an important strategy. However, when studying the more central parts of the brain involving cognition, the limitations of a strict stimulus response strategy become apparent. The ultimate goal of brain research cannot just be uncover correspondences between external signals and neuronal responses. Building a dictionary of representations from scratch would be an enormous effort, but it is easy to see why such a program has limited success. The outside-in approach interrogates brain circuits by asking what those circuits can potentially do, rather than what they actually do. potentially do and actually do. It's a big difference, which produces an illusory understanding of brain computation. Overall, I suggest that searching for alternative approaches is warranted. The essence of complementary strategy I suggest is simple. Understand the brain from within. In this inside-outside framework, the key issue is the mechanism by which stimuli and situations become meaningful percepts and experiences for the brain. The main emphasis is how the brain's outputs, reflected by animals' actions, influence incoming signals. By linking an otherwise meaningless brain pattern to action, that pattern can gain meaning and significance to the organism. Within the brain, the emphasis is on how downstream networks make use of the messages obtained from their upstream partners. In this framework, the goal of the brain is to explore the world and register the consequences of successful exploratory actions to improve the efficacy of future actions. Thus, an action-perception loop learns to make sense of sensory inputs. Perception, thereby, is what we do, not the potentiality. Nearly all chapters of this book revolve around an action-centered brain, because I want to make it as clear as humanly possible that no meaning or advantage emerges for the brain without the ability to calibrate neural patterns by behavior-induced consequences. Without generating outputs to move and optimize the senses and calibrate brain circuits at some point in our lives, I claim no perception or cognition exists. A major advantage of inside-out approach is that it is free of philosophical connotations. It takes brain mechanisms as an independent variables, as opposed to attempting to find correspondences between subjectively derived categories the William James ones that we all slave under, end of quote, and brain responses. Brains largely organize themselves rather than being enslaved to input signals. I'm interested in how internally generated self-organized patterns in the brain acquire meaning through action, which becomes what we call experience. Instead of looking for correlations between experimenters' selected signals and activity patterns of neurons, we should ask a more important question. How does those firing patterns affect downstream reader neurons? We can call this strategy the neural observer or the reader-centric view. Before you accuse me of simply replacing the homunculus with the reader, please consult chapters 4 and 5. The term reader-observer is meant to be an engineering term, referring to an actuator that responds to a particular pattern of upstream neural activity, but not to others. Only a particular bunch of keychain opens a particular lock. In the subsequent chapters, I'll give you a taste how this is done in the brain by discussing a set of recent findings that illustrate progress toward an inside-out research program. Just let me put in a footnote here. Interactions between the body and mind was natural to the Greek philosophers. Aristotle might have said that we learn about the world by our actions on it. Only after the concept of the soul fused with the mind came the full separation, especially with Descartes' declaration of the independence of res extensa and the God-given res cogitans. Perhaps Henri Poincaré was the first thinker who speculated that the only way sensations become relevant and turn into experience is by relating them to the body and its movements. It's a quote from Poincaré. To localize an object simply means to represent oneself the movements that would be necessary to reach it. How good. Thank you, Henri Poincaré. Blank paper or pre-existing constraints? That's the question here. The choice of outside in and inside out, action-centric frameworks also shapes our ideas about fundamental brain operations. One of the oldest outside-in views was formulated by Aristotle, who suggested that we are born with a blank slate, tabula rasa, on which experiences are written. The tabula rasa view is an almost inevitable assumption of the outside-in framework, because under the empiricist view, the goal of the brain is to learn and represent the truth with its veridical details. This view has influenced thinking in Christian and Persian philosophy, British empiricism, and the Marxist doctrine. and it has become the leading school of thought in cognitive and social sciences. Similar to the free will idea that humans can do anything, tabula rasa thinking implies that anything can be written on a blank brain. Although I have never met a neuroscientist colleague who would openly subscribe to the tabula rasa view, many experiments and modeling studies today are still performed according to this associationist philosophy-based framework. Very important. Associationist philosophy-based framework, or its modern-day version, connectionism, not to be confused with connectivism. The main idea of connectionism, especially in cognitive psychology and artificial intelligence research, is that perception and cognition can be transcribed into networks of simple and uniform neurons, which are interconnected relatively randomly with large similar synaptic connections. Nothing is further from the facts. I will explain it later, but briefly summarize here. Early behavioral observations already argued against the idea of the brain as a blank slate. Researchers demonstrated repeatedly that animals do not associate everything equally and cannot be trained to do all tricks the experimenter expects them to do. Behaviors that relate to the animal's ecological niche can be trained easily because the brain is predisposed or prepared to do things that have survival or reproductive advantage. For example, spontaneous alternation, the tendency in rodents to choose different paths during foraging, is an instance of biological preparedness for the rapid acquisition of species-specific learning. Returning to the same location for food within a limited time window is not an efficient strategy, because choosing an alternative route will more likely lead to reward. In contrast, associations that would be detrimental to survival are called contra-prepared. For example, it is virtually impossible to train a rat to rear on its hind limbs to avoid an unpleasant electric shock to the feet, since rearing is an exploratory action and incompatible with the hiding and freezing behaviors deployed in case of danger. How interesting, I had no idea. A practical message here is that if training takes weeks or longer, the experimenter should seriously consider that the brain signals associated with such extended shaping of behavior may not reveal much about the intended question, because each animal may use different tricks to solve the task, and these may remain hidden for the experimenter. Neuroscience has also accumulated much experimental evidence against the tabula rasa model. The most important is the recognition that a great deal of activity in the brain is self-organized instead of being driven by outside signals. This self-generated persistent activity is supported by the numerous local and brain-wide neural rhythms, which we discuss later. For now, it is sufficient to note that these oscillations are not only part of and help us to stabilize neural dynamics, but also offer a substrate for syntactical organization of neural messages. Each period of an oscillation can be conceived as a frame that contains a particular constellation of spiking neurons. Metaphorically, we can call it a neuronal letter. In turn, the cycles of the many simultaneously acting oscillations can concatenate neuronal letters to compose neural words and sentences in a virtually infinite number of ways. This brain syntax is the main focus of discussion in chapters 6 and 7. Wide-range distributions, good enough and precise solutions. As an alternative to the empiricist outside in tabula rasa view, I raise the possibility that the brain already starts out as a nonsensical dictionary. I like his wordings. It comes with evolutionary preserved, pre-configured internal syntactical rules that can generate a huge repertoire of neural patterns. These patterns are regarded as initially nonsense neural words, which can acquire meaning through experience. Under this hypothesis, learning does not create brand new brain activity patterns from scratch, but instead is a fitting process of the experience onto a pre-existing neural pattern. Swedish educational system and most Western educational systems are all based on the idea of tabula rasa. And in ordinary language, we are all empty. We are all born empty. And I think the Greek tradition is in that way as well. We take it as a part of reality that we are all born blank. The pre-configured brain is supported by a mechanism I refer to as high diversity organization. Diversity and large variations are the norm in the brain, whether we are analyzing its microscopic or macroscopic connectivity or dealing with its dynamics at a small or a large scale. Neuronal firing rates, connection strength between neurons, and the magnitude of their concerted action can vary by 3 to 4 orders of magnitude. I speculate that this diversity, which respects a logarithmic rule, is the essential backbone that provides stability, resilience, and robustness to brain networks against competing requirements for a wide dynamic range, plasticity, and redundancy. There are many advantages of a pre-configured brain over the blank slate model. The most important of which is stability of brain dynamics, because adding new experience after each learning event does not perturb much the overall state of neuronal networks. I will discuss that even the inexperienced brain has a huge reservoir of unique neural patterns, each of which has the potential to acquire significance through the experience of unique events or situations. The tales of these wide range distributions, such as neurons with high and slow firing rates and strong and weak synaptic connections, can support seemingly opposing functions, such as judging a situation as familiar or novel. Neural circuits involving a minority of highly interactive and well-connected neurons may appear as a constraint. However, the benefit of such apparent constraint is that the collective action of such oligarchic circuits with skewed distribution of resources allows the brain to generalize across situations and offer its best guess under any circumstances, so that no situation is regarded as completely unknown. I call this aspect of neuronal organization the good enough brain. The good enough brain uses only a small fraction of its resources, but its member neurons are always on the alert. On the other hand, the remaining majority of slow-firing member neurons with weak synaptic connections have complementary properties, such as high plasticity and slow but precise, reliable processing. This other extreme of network organization compromises the precision brain, whose main job is to redefine a situation or an event and determine its distinctness in high detail. The good enough and precision aspects of brain organization complement and in fact assume each other. In the pre-configured brain model, learning is a matching process in which pre-existing neural patterns, initially nonsensical to the organism, acquire meaning with the help of experience. As discussed earlier, attaching meaning or significance to any neural pattern requires grounding, which can be provided only by action, the ultimate source of knowledge, in contrast to the tabula rasa model, in which the complexity of neural dynamics scales with the amount of experience. In the pre-configured brain network, homeostasis is only minimally and transiently affected by new learning because nothing is added to the circuitry. Only rearrangements takes place. The total magnitude of plasticity in brain circuits and the overall spiking activity remain constant over time, at least in the healthy adult brain. I make no claim that my strategy is definitely right, but the alternative formulation that I'm suggesting might provide different insights than the current representational framework. In contrast to the pre-configured brain, the outside-in framework assumes that there are obvious things in the outside world, which we often call information, and the brain's job is to incorporate or absorb that information. But how? The brain codes information, or does it? This often heard statement should communicate a lot of content to everyone. After all, we live in an information age in which everyone is familiar with such terms as information and coding. But when we attempt to explain and define information coding in the brain, we pause because we do not have a widely accepted, disciplined definition. When terms are not defined precisely, they often acquire many disguised interpretations and therefore convey different meanings to different individuals. Is my grant proposal rejected or approved? From the perspective of information theory, the answer represents a single bit of information, yes or no. But for the receiver of such information, me, it induces profound and long-lasting changes in my brain. While the mathematical formalism of information theory is neutral to information content, the same cannot be said for the brain. For a behaving organism, decoding information cannot be divorced from meaning, the experience-based prediction of potential consequences of that information. There is no such thing as an invariant information content in a stimulus. How good. Features or attributes of a stimulus are not objective physical characteristics of the stimulus. Instead, the relevance of the stimulus depends on changing internal states and the brain's history with similar situation, not a blank slate. In the following chapters, I hope to show you that the situational relevance is not a small matter, but has a profound and observable effect on the nature of neural activity and its relationship to the sensory environment. The same visual stimulus evokes very different neural patterns in a frog's brain, my brain, or the brains of other humans. The induced pattern even in my brain depends on its current state. If the letter arrived the same week when I received the news about other rejections, it would induce a different effect compared to an alternative situation when the letter arrived a day after I won the lottery jackpot. Computation performed by computer programs or machines is referred to in general as information processing. In reality, the information is not in the processing. It becomes information only when the interpreter by an observer that recognizes its meaning and significance. A computer program can effectively control a robot or other man-made machines, thus giving rise to the illusion that information resides in the program. However, the process is based on a human-designed solution, even if it involves a complex trial and error learning process, including deep learning in artificial intelligence programs. In short, information is not inherent in computation, in machines or brains or anything else, but becomes such when it is interpreted. In neuroscience, information is often understood as acquired knowledge, a broader concept than in information theory. Claude Shannon warned us that information theory is aimed in a very specific direction, a direction that is not necessarily relevant to such fields as psychology. I will discuss why the brain is not an information-absorbing, perpetual coding device, as is often portrayed, but a venture-seeking explorer, an action-obsessed agent, constantly controlling the body's actuators and senses, the submotor system, to test his hypothesis. The brain ceaselessly interacts with, or rather than just detects, the external world in order to remain itself. It is through such exploration that correlations and interactions acquire meaning and become information. Brains do not process information, they create it. Now let me try to give a broad definition of coding as it applies to the brain. In essence, coding is an agreement for communication between the sender and receiver, making the content of encoded information a secret to outsiders. If the code is not known to the receiver, the packets carry no inherent information. There are many forms of coding, but the fundamental features remain the same. The encoding-decoding process is done via a cipher, a transforming tool that encrypts messages by mutually agreed syntactical rules. So the information looks like nonsense to the uninitiated. Encryption is not always intentional, of course. Sometimes it just happens. Evolution has no aim of secrecy, yet biological codes are often mysterious to us. That is, until we uncover the cipher. In the outside-in philosophy, the words in James's list are the senders, and the brain is the receiver. However, terms such as emotion, will, attention, and others are not senders of anything and possesses no inherent information. Space and time are not sensed directly by the brain either, and no messages are being sent by them. If we want to understand information, we should start with its creator, the brain. Code-breaking exercises. The American writer Edgar Allan Poe, whose hobby was cryptography, believed that human ingenuity cannot concoct a cipher which human ingenuity cannot resolve. But modern science claims that it is possible to encrypt messages that no human or machine can break. Does the cipher of brain dynamics fall into this highly secured category, or can it be outsmarted? As we search for ciphers in the brain, we may learn from previous deciphering successes. The Englishman Thomas Young and the Frenchman Jean-François Champollion are credited with deciphering Egyptian hieroglyphics by using a written cipher, the Rosetta Stone. This is the most famous artifact of the British Museum. Contains the same script in 3 languages: Greek, Demotic, and hieroglyphics. As a polymath, Young's strategy was to find correspondences of well-known names of gods and royalty, such as Ptolemy and Cleopatra, between the words in the Greek text and the glyphs. This approach provided fast initial progress, but could not uncover the generative rules of hieroglyphic language. That task needed Champollion's genius and his understanding of syntactic roots in Hebrew, Syriac, Greek, Arabic, Aramaic, Persian, and critically Coptic and Demotic. he hypothesized that phonetic signs were not just used for the names of royals, but also represented a general rule. This insight suggested that Egyptian hieroglyphs could be read and understood by transforming the glyphs to sounds and concatenating them. Thus, the nonsensical messages of a forgotten language became information. Without the Rosetta Stone, the secrets of Egyptian hieroglyphs might well have remained forever hidden. My second example of a cipher is connected to the most celebrated codebreaker, Alan Turing. A genius by many accounts, he and his team at Bletchley Park, north of London, are credited with breaking the code of the secret messages of the German Navy in World War II. With all my admiration and respect for Turing's contributions, I must make a correction. Neither he nor his team broke the code. They received the cipher, the key syntactical tool of encryption, in the form of the Enigma machines, from the Polish Cipher Bureau early in the war. Without this access to the syntactical rules of cipher, the secret messages sent to the German U-boats by the Kriegsmarine headquarters would likely have remained gobbledygook to the Allies. Alan Turing's Rosetta Stone was the Enigma's hardware. Is deciphering a secret code possible without some a priori knowledge of the syntax? Our third example, discovery of the genetic code and the translation of DNA to RNA to protein, was such a case. The cipher in this case was the double spiral, which is also following the golden ratio. The two strands of the helix consist of polynucleotides made up from simpler units of nucleotides. Each nucleotide is composed of a nitrogen-containing nucleobase, cytosine, guanine, adenine, or thymine, as well as a monosaccharide sugar called deoxyribose and a phosphate group. The syntax is elegantly simple. A is always paired with T, and C paired with G, providing the rule for making the double helix DNA. The hydrogen bonds between these match pairs of nucleotides bind the nitrogenous base of the two separate polynucleotide strands. This DNA sequence is ultimately translated into a string of amino acids, the building blocks that make up proteins. This is done via RNA, which transcribes a particular set of 3 nucleotides into a particular amino acid. Using this messenger RNA as a template, the protein molecule is then built by linking neighboring amino acids. These examples of code-breaking practices and their players offer an important lessons for brain scientists in our search for a neural code. When the syntax is known, breaking a code is a hopeful exercise. Uncovering the meaning of hieroglyphs took a few thinkers and a few decades of hard work. A few years of nerve-wracking search for correspondences, with several hundred people working together, were required to decipher the messages encrypted by the Enigma machines. Even though the cipher was available. In the case of the genetic code, with well understood goals, the efforts of several hundreds of scholars over the span of few decades provided a mechanistic explanation for a miracle of nature, the hypothetical force that produces complex organisms from simple seeds. So what should be our strategy for identifying the brain cipher? Collecting correspondences and correlation is not enough. We also need to understand the neuronal syntax and to ground our correlational observations with a firmer second opinion. Only with such independent knowledge can we hope to figure out the secret meanings of the brain's vocabulary. At this point, the reader might rightly ask, why does it matter to logically proceed from the inside out rather than the other way around? Doesn't it amount to the same thing in the end? In and out and out and in. Can we not understand relationships either way? Answering this will require discussion on the complex problem of causality in neuroscience, a topic for the next chapter. So, summation of the first chapter of the book by first György, and then I will make a sort of recap of what we went through in this lecture and also add some of the previous lectures. Here, summary. I presented some contrasting views and research strategies that can provide complementary knowledge about brain operations. The first comparison was between outside-in and inside-out strategies. The outside-in or perception-action framework has deep philosophical roots, starting with Aristotle and most explicitly elaborated by the empiricist philosopher David Hume. According to this framework, all our knowledge arises from perceptual association and inductive reasoning of cause and effect relationships. This philosophy is foundation of Western science and continues to influence thinking in contemporary neuroscience. An inevitable consequence of this perceptual representation-centered view is the assumption of a hidden homunculus that decides whether to respond or not. In contrast, my recommended inside-out framework takes action as the primary source of knowledge. Action validates the meaning and significance of sensory signals by providing a second opinion. Without such grounding, information cannot emerge. Next, we discuss the relationship between tabula rasa and pre-configured brain models. In the empiricist outside-in model, the brain starts out as a blank paper onto which new information is cumulatively written. Modification of brain scales with the amount of newly learned knowledge by juxtaposition and superposition. A contrasting view is that the brain is a dictionary with pre-existing internal dynamics and syntactical rules, but filled with initially nonsense neural words. A large reservoir of unique neural patterns has the potential to acquire significance for the animal through exploratory action and represent a distinct event or situation. Distinct, I will say that, yeah, I'll come to that later. In this alternative model, the diversity of brain components, such as firing rates, synaptic connection strengths, and the magnitude of collective behavior of neurons, leads to wide distributions. The two tails of this distribution offer complementary advantages. The good enough brain can generalize and act fast. The precision brain is slow but careful and offers needed details in many situations. So a summary for this rather long chapter. (16 to 17 the pages and the paragraph, what about internal observers? This is a clear kill-off from the subjective side. Now we got a second weapon. A second front is opened in the massive coercive attack on Cartesian dualism. Before, we had mainly the object side. Quantum mechanic. James Gibson is actually on the outside because his philosophy is an attack on the outside object part of reality, leading to the inside, but it's still starting from the outside in a more clever manner. But this is strong. This is really strong material. And it also shows why we cling to the classical mechanical idea, why we cling to the Cartesian duality, is because once we start trying to work our mechanisms, our organisms to this, the lack that becomes evident, the malfunctioning of the system, because we cannot have information without going into our own system. If we think the information is out there, this is where we're going to put our actions. Is that understandable? because we need to put our actions here. This is the only place you can understand it. And this, oddly enough, helps me with the understanding of Gödel's mistake by Ashish Adela after all these years. I read it through and through. But he showed that meaning needs to be added for mathematics to be understood. And his term meaning is the action in György. Without moving about, without doing the gestures, we will not have understanding. And Gödel simply didn't understand mathematics. It's a harsh argument, but it's true. Mathematical signs can only have meaning if they are connected to the action. If this is not involved from the observer, from Gödel himself, he will not have access to mathematics. It is not only out there, it is out there and in here, 100% in both directions. And to have both, to access to both, you need to take both into consideration. And if you get stuck on the outside model, you will have less of understanding, because you will start to move about less. Your action in here and out here will be less, and therefore less understanding. In a very fine detail, this is what Ashish was pointing to. I would say it was really hard to understand. This helped, but he was a little bit too careful, and I simply didn't understand his associations. And I'm not sure if anyone else did as well. Siprubegu, I don't think he did. But this is clearer. This is more expanded, and by opening up this new door, I feel already liberated. I feel that we can see the world clearer. We understand how the world can be a 100% shared and objective, and also can be subjective. And I also understand the reason we don't reach in an objective world, which is proven by so many neurologists, is because of the Cartesian dualism. Our fixation with objects out there hinder our access to the real shared world. And we do not share world anymore. This is a proven fact. This is what we need. This is the foundation. We know that. Way too much research has all shown we have not access to a communal world. And we also know we used to do. And as coming from Ian McGilchrist, so clear indications in this biggest collection of research detail, it will also lead to states where you have even less access to an objective, independent world. State like autism, schizophrenia. Schizophrenics all say that objects only have one meaning, and that they are strictly out there. And they have very little access to the world. They are non-aware. It's a sad state, but it is the state of the modern world, going away from reality. And without bringing this up and clearly understand it, I would find better formulations or easier formulations. We can further ourselves. This is a health thing. It is incredibly unhealthy. It is detrimental to yourself. And as György writes in another chapter, you can't plan anymore. You can just imitate planning from others. And you become more or less a slave. A complete slave to the ones, the few today, who are in absolute command of what György writes. There are a few, maybe a 5%. They are living in the real world. They are doing the business. They are making decisions quickly in the action-based, having access to reality. Because if you don't have access to reality, how can you make sense to others? if you're stuck with a private language. You can't even understand yourself. Autism, schizophrenia, cannot understand themselves, their inside. I think this connects very neatly with Ian McGilchrist. The brain is action devised, and that doesn't mean moving about. It doesn't mean going about to do things, but it's clear. How could one understand a cup of coffee without moving your hand towards it? And how can other people understand what I'm doing without having access to this gesture? It is an integral part, and it's not ever a 0 and 1 perspective. You know ever either right, wrong or right. There's always a scale. And the scale is what leads to an absolute 1 and 0, not vice versa. That's another way of explaining the outside inside start with 1 and 0 and ends up with having no absolutes. The inside out starts with a scale and manage to have absolutes, absolute truths. Those are not possible if you don't see where the meaning is coming from. And we know having this model takes away reality, and then you can get stuck even more in the mechanical idea. That's the only chance. If you live in reality, if you're interacting with the precepts, having meaning, effectively, even if you claim it yourself, you will not be a mechanical constructed realist. You will not be a reductionist. You will not be a Cartesian dualist. It is incompatible with being an effective planner, being effective in life, being high up on the hierarchy, and being a Cartesian dualist. It's completely incompatible. Ian McGilchrist didn't find one single case. It cannot exist. Likewise, underneath, it's almost impossible not to be a Cartesian dualism. This is being the slave. This is being the receiver of orders. So Brave New World, as Aldous Huxley, is clearly being depicted in the most clear way by György in this wondrous introductory chapter. Tabula rasa is also interesting. Tabula rasa is not a separate idea, I would say, in Cartesian dualism. It is necessary to build up the whole lock, to become locked in this. It's a part of the lock. Once you start with the outside, then you will come to the conclusion, as James Locke, as Hume, as all the British empiricists, that we were a blank slate from the beginning. So you see how different views interlocks. You cannot unlock one only. You need to do them simultaneously. And you also need to do it somewhat inside the subject side and the object side, quantum mechanics, neurology at the same time. It's a simultaneous opening up. If you leave one of the cogs unattended, you will somehow mentally, physically remain in classical physics. Because it's first when you have all the cogs, the new sense come to view. And then you start living in the world, you start interacting with other people, you start making sense. And then, of course, you will never, there's no turning back. But until you made that change, it takes some effort, it takes some trust. And György, I would say, he provides most excellent trust in that things are sane and whole once more. And this is the working of the brain. How could it work any in anyone else's way. Homunculus. Once you have the homunculus, you also have the panopticon out there. Maybe they are related. One is cousin to the other. I don't know. But don't make do. Don't stick to these nonsensical things, because it's a sad life to have those. Take those as pointers. Let the panopticon wake you in the morning, and the homunculus toss you to bed when you go to sleep. In the end, you will give them up, and you will feel much, much better. I can't wait until chapter 2 of the book. I say thank you very much, and have a very pleasant afternoon. Bye-bye for now.